ready? Gracias. Empezamos. So, we're going to start. Good morning, everybody. It's a pleasure to introduce Dr. Francisco Kitaura from the Leibniz Institute of Astrophysics in Potsdam. Francisco did his PhD at the Max Planck Institute under the supervision of Professor Simon White. And after that, he moved to Italy with a Marie Curie fellowship. He was working in the group of Andrea Ferrara, both at CISA and the Scuola Normale Superiore. And after that, he returned to Germany. He was for 1 year, again at MPA, with funding from the Cluster of Excellence and the Max Planck Society. And then it was in 2011 that he got the Karl Schwarzschild Fellow, and he moved to Potsdam, where he's now. Francisco, well, he's an expert in large-scale structure, and for example, just to give you quickly a few notes, he's the PI of the cosmology science case in the Foremost project, and he's leading some of the working groups, or co-leading some of the working groups that are related to projects like Euclid or JPass or BOSS. Today he's going to talk about his work on modeling the large-scale structure. So thanks for visiting us.
So thank you very much for inviting me and for the nice introduction. I want to first thank also the students announcing this talk for conceding me the professor title, which I don't have. Okay. So let me talk about how to model and infer the cosmological large-scale structure. Due to the complexity, we need some effective bias, and I will discuss this. When we look at the primordial fluctuations of the universe, we know that it is a very homogeneous field, closely Gaussian distributed. Maybe some primordial non-Gaussianities are present, and those would be very interesting because they would reveal the mechanism in which the Big Bang producing an inflationary process, these primordial fluctuations from which all the structures we observe today have arisen. So if we use some n-body simulation and we let it evolve, then we see how these Gaussian fluctuations form a cosmic web with filaments, with clusters, halos, and voids, walls. So a complexity which is not present in the initial conditions. And this is already hinting at the difficulty we have in analyzing the data. So this is highly non-Gaussian. It is not possible anymore to fully characterize the structures with the two-point statistics with the cosmic variance. We need higher order correlation functions. Gravity has coupled modes, etc. So, as I was saying, gravity couples different modes. It acts on distances and introduces a strongly non-Gaussian cosmic web. Then we have also the problem of shell crossing. So essentially, if we think of matter tracers from the initial conditions, when they evolve, then they may get very close positions but completely different peculiar velocities. So that is also a problem, the so-called multi-valued problem. And then we have what we are really observing are luminous tracers. So we have a discrete sample. And on top of that, we have, of course, observational systematics like the survey geometry, radial selection function, peculiar motions of the galaxies which are on top of the Hubble flow expansion, the so-called redshift space distortions. All these problems we need to face them. And regarding the fact that we are dealing with discrete samples, I should mention that we have an information loss. We don't have the full dark matter field, but we just have some, not only bias tracers, but it's not just a nonlinear complex relation, there is an information loss there. Okay, so that's my motivation to say that we need a statistical inference approach, and the accuracy of the inference analysis will depend on the statistical assumptions, our physical models, etc. So let me start in the first part discussing how to model the cosmological large-scale structure with effective models. One of the problems is gravity, how to model structure formation. And if we want to do this in a very efficient way, we know that we need to solve the Vlasov equations in reality. In principle, there is baryonic physics, there is also a feedback processes and a variety of complex processes. But if we just think about the formation of structures of the dark matter field, and we need to model this in an inference analysis in a very efficient way, we need to explore approximate methods. So essentially, these are characterized by the relationship between the divergence of the displacement field, which suffer particles from the initial conditions until the final ones, and the initial Gaussian field. If we assume a linear relation, that's called the Zeldovich approximation, or linear Lagrangian perturbation theory. Of course, you can go to second order, even to third order, fourth order, fifth order. There are papers on all this. The point is that second order is important because it's including tidal fields, which are relevant to model the structure formation. However, if one runs a second order Lagrangian perturbation theory, you will see that clusters are puffed up, that the filaments are not accurately modeled, etc. There's a lot of artificial shell crossing. Nothing impedes particles prevents particles from cross each other and not notice each other and continue their path. However, if we continue, we can improve those models with corrections derived from, for instance, the spherical collapse model, and we can very much resemble the relationship one would get from n-body simulations. So essentially here, you see that this would be high-density regions. There is a negative sign, but there is also a negative sign here in the overdensity. So these are the high-density regions. These are the low-density regions. And in the high-density regions, there is like a there is like a threshold impeding structures from continue particles from continue moving. Right here, nothing prevents particles from continue their paths, but here you see in n-body simulations that there is this cutoff. And you can model that. You can also improve this nonlinear relationship. You can see here the mean of this relationship. So you can improve things, and then you get this kind of result, which resembles much better n-body simulations. Also, I should mention that there are interesting developments in speeding up n-body solvers effectively solving the Vlasov equations by using approximate perturbation theory solutions as a first step, and then computing only the rest with full n-body simulations, and that could save you a factor 100 of steps in n-body simulations. So, okay. We have some models for modeling in an efficient way the dark matter structures, at least on large scales of a few megaparsec. Now the next difficulty is to model the relationship between the dark matter density field and, say, the halo density field or the galaxy density field. And this is already an artificial concept, a mathematical construction, because essentially what you have are discrete samples, number counts maybe, if you subdivide your volume in volume elements. But we are asking ourselves about the expected number counts of those tracers, all right, to make this clear. So this is not an integer, this is a real number. And we can follow this model and say, all right, there is a bias relation which is arbitrarily complex. Now, which kind of information do we need if we, say, parameterize some kind of model to characterize that bias relation? And unfortunately, or fortunately, we find out that we need, in fact, all the higher order correlation functions. So it's not sufficient to just write a model and fix it, for instance, with the power spectrum with the 2-point statistics, but you will need higher order statistics. And I will show this in a minute. So for instance, a very powerful and accurate model, as I will show, is this one, where you have a power law for the relation between the dark matter density field and the expected halo density field. You need some threshold bias telling you, modeling precisely what I was describing before, that there is an information loss, that you don't have the full dark matter density field anymore. You're focusing, say, forget now about galaxies. If we focus on the gravitationally collapsed objects like halos, then we have to throw away all the dark matter particles which are not related to those halos. So there is an information loss, and this is essentially the threshold bias already discussed by Kaiser in 1984. And you can, in principle, improve that model by saying that threshold is an exponentially decaying function. And then finally, we have to introduce, again, an artificial concept, which is the stochastic bias. And I say artificial because what I was showing before is a deterministic process. So the real intrinsic stochasticity is in the initial fluctuations, which we believe are quantum, have come from quantum fluctuations. And then were frozen, stretched out, and have set these primordial fluctuations from which gravity has evolved and produced the structures we observe today. But since there is this information loss, we need to deal with these stochastic models and to produce this integer counts, number counts in volume elements. And that is not trivial because it depends, it's not just a Poisson process as it is commonly modeled. It is deviating from Poissonity, and this was already found out by Peebles in 1980, because there is either a correlation or an anti-correlation. Only in special cases it will be a perfect Poisson distribution, meaning that there is no correlation at all inside those cells. So if you take a volume element, say, of a few megaparsec cube, and you're sitting inside that volume element and you have a galaxy, there is an excess probability of finding another one. If you're talking about very massive galaxies and you're taking very small volume elements, you may have an anti-correlation. There is not enough matter left to produce another very massive galaxy. Then you would have an anti-correlation, and that would be a sub-Poisson process and not exceeding the dispersion of Poissonity. And these things have been analyzed in embodied simulations by a series of people. So this is actually known, but usually not modeled in the analysis. And I will show later on that this is actually important and will affect summary statistics that we use in cosmology. Okay, let me move on. Yeah, well, here I'm mentioning already that it could have a 10% effect in the 2-point statistics at scales relevant to baryon acoustic oscillations. And even larger if we are talking about less massive objects where you can have even more objects inside such a volume element. And maybe you can already see that this kind of description will depend on the resolution we are working on, whether we work with very large volume elements or smaller volume elements. But since we want to analyze the data in an efficient way, we don't want to go to the highest resolution. That's computationally maybe not affordable. And if we need this effective, and then, by the way, all these approximate gravity solvers will break down below a certain scale. Maybe with COLA we managed to do much better, but essentially if we don't do a full gravity solver with very high precision, we will not manage to really resolve all the objects we need for future surveys, which can go to very low masses. So we need some kind of scale, which I think we can call large scale if we talk about megaparsec scales or so. That's already kind of a large scale, because you can have 10 luminous red galaxies inside such a volume element, or even hundreds of galaxies if you go to lower masses, okay? Well, this is just to show you that people have been investigating in n-body simulations this nonlinear relationship between the expected halo density field and the dark matter density field. This was interesting because they essentially took the same large-scale phases and changed just the small-scale phases and run hundreds of n-body simulations sharing the same large-scale phases but changing the small-scale phases. So they would produce different halos with the same large-scale density field. And that enables them to study the expected halo density field, because they can do statistics with those hundreds of n-body simulations. Usually if you have just one n-body simulation, you have a particular realization of that halo density field. And as I was pointing out, it's not the same, the realization of the halo density field and the expected number counts of the halo density field. And by the way, this applies also for galaxies. It's just an additional bias between the halos and the galaxies. All right, you can see that this threshold bias changes when you consider different mass bins, 10 to the 9 to 10 to the 10, 10 to the 11 to 10 to the 12. So it's on high densities. Towards high densities, a power law is a very good approximation. Towards low densities, you need this threshold, and an exponential cutoff is even more accurate. So is this the end of the story? Well, as I was already hinting before, we really need to take into account higher order statistics. So in this exercise, we took a reference catalog from a full n-body simulation. This would be the black line, and they are very much on top of each other, the blue, the red, and the black. So the blue curve would be the power spectrum, the two-point statistics in Fourier space. So these are different scales. Here you have the smaller ones, here you have the larger ones. You can already see the baryon acoustic oscillations there. And because we are considering a very large volume, 2.5 gigaparsec per h cube volume. So the statistics is good. And essentially, we tried to reproduce the two-point statistics with different sets of effective bias parameters. One, neglecting this threshold bias I was mentioning, which is known in the literature, and one, considering it. So both in terms of two-point statistics do a good job. However, if you look at the bispectrum, which are essentially throwing triangles in Fourier space, so the three-point statistics in Fourier space, you will see that the black n-body simulation, represented by the black arrow bars and points, is in good agreement with our model, including threshold bias, but is very off. The solution is very off if we ignore it, right? So this is telling you, in terms of two-point statistics, we may have degenerate bias parameters, and we need to go to higher order statistics. Okay, so this is really an indispensable ingredient. Now, this is actually not the whole story, because we also need to take into account tidal fields, which have decoupled essentially the dark matter field from the halo expected density field. So essentially, the mass is not only determined of a certain halo, not only determined by its local density, but also from its environment. And we can add, in this bias description I was telling, local and non-local terms. Actually, this has been introduced, this formalism by MacDonald and Roy in 2009 and has been studied in body simulations in a very active way, but by various groups. The thing which had not been done was to actually use those models and produce catalogues implementing those models. So usually you just look at how those models will have an impact in the 2-point statistics and the 3-point statistics by writing this down and comparing with embodied simulations. But actually, if you want to test those models, you can say, okay, let me try to use them in a very practical way, implement them, and produce halo catalogues and compare with embodied simulations. So it's a more direct way. And actually, what you can see is that if you just consider large scales or intermediate scales, actually, the non-local bias is degenerate with the stochastic bias. It gives more power. So you tune your non-local bias on, and you give it more and more, and you will get more and more power. The same happens if you say the deviation from Poissonity is larger and larger and larger. So the clustering is larger and larger and larger inside these volume elements. This is what's happening here. However, towards small scales, you see that they are actually not exactly degenerate. Here, essentially, you can see the shot noise. Oh, I should mention that this is the power spectrum times K, times the K modes, because in that representation you can better see these baryon acoustic oscillations, which we are interested in. So one of the motivations actually is to very accurately model baryon acoustic oscillations through this method, with these methods. Okay, and actually, we need to even consider more things. I already discussed them a minute ago. What I was presenting until now was only the way to populate a dark matter density field with a very large mass bin of different populations of halos. Now, we could, in principle, consider subpopulations of halos, but we would run into a problem because then certain mass populations of halos would be underrepresented. We would have a lot of noise. So it's better to consider the full population of halos, considering all, and then in a post-processing step, which I will describe now in this slide, assign to those halos their properties, their masses, and so on. And then this is a statistical question. So if I have a 3-dimensional distribution of halos, and you can do this exercise with an n-body solver, where you have the halo catalog, and then you just erase the column telling you the mass of those objects. So you have those 3-dimensional, just the positions in 3 dimensions. You have the density field, okay? So let's assume you have the large-scale density field, on a few megaparsecs. So you don't really have the information of the masses of those objects. And then the question is, what information, what else do you need? Well, given some set of cosmological parameters and given some redshift, some snapshot, what else do you need to be able to accurately assign those masses to those objects and reproduce the 2-point statistics for arbitrary mass bins, and also the 3-point statistics, well, the 2-point statistics in Fourier space, in configuration space. What do you need? And the answer is, as we were discussing already, well, you need more than just say the mass function. The mass function is telling you how many objects you have of a certain mass inside that volume for a given cosmology and a given redshift. But you need more. You need the local density, and that's not enough. You need even non-local quantities, like the tidal field. So we do a cosmic web classification considering the eigenvalues of the tidal field. If they are all positive, this is a collapsing region. If they are all negative, that's an expanding region, and so on. And using that information, we are already much, much better. However, we found out that for very massive objects, and I already mentioned this before, that's not sufficient. You have to take into account that there is this exclusion effect. There is not enough matter for very massive objects to be close together. So we need to consider also this separation between the objects. And then we managed to really do a good job in terms of reproducing the statistics of those objects, assigning the masses. I will show in a second how we can also apply this, extrapolate this to stellar masses and have applied this to observations. So essentially, let me just describe this plot, which is the only one I did not describe, which is the relationship between the local density and the maximum circular velocity, which is related to the mass of a halo. And if you look carefully, you will see that very massive objects seem to have some kind of relation, but for less massive objects, in lower density regions, so in very high density regions, you will find only massive objects, but in lower density regions, you may find objects of any kind. And actually, even in high density regions, you may find very low mass objects. There is room for them. Well, so this is the application we did for the BOSS survey here, and this is already going to stellar masses. I should mention that my collaborators in this project, Hye-Sun Chuang, Sergio Rodríguez Torres, Cheng Zhao, Francisco Prada, Gustavo Yepes, Anatoly Klipin, and so many people from the BOSS collaboration who were really helping a lot in this project, have done a wonderful job. In particular, let me highlight the work done by this group in Madrid, Sergio Rodríguez Torres, under the supervision of Francisco Prada and Gustavo Yepes, producing with high resolution and body simulation very accurate reference catalogues, which I can use then to calibrate my effective bias models. And what they did was to apply halo abundance matching, including a scatter to be precise, for a lot of snapshots reproducing the data of the BOSS survey. And that was very useful for our work, where we then managed to produce thousands of mock catalogues. Let me just mention that this is the largest effective volume which has been ever simulated, and also the largest effective number of particles. So essentially, if we would have used conventional methods, this would have taken 9 billion CPU hours. So one M-body simulation took 2.3 million CPU hours, and you need thousands of them. And in reality, with these effective bias models, it took 0.5 million CPU hours. In 1 week at Mare Nostrum, all the thousands catalogues were done. So on the left-hand side, you see the Southern Galactic Cap, the Northern Galactic Cap of the observations of the BOSS survey, ranging from 0.18 till 0.75 in redshift. You see that you have kind of ring structures because the stellar masses change due to the selection function. And you see also the survey geometry. And here on the right-hand side, you see one of such galaxy catalogues. So at first glance, mocks are indistinguishable from observations in a statistical sense, but of course you have to quantify this. And what we looked at was, for instance, at the correlation function in redshift space, the monopole, for different stellar mass bins, the analogous exercise as we did before with halos. And you can see that we perform very well for low mass bins, a little bit worse for high mass bins. This kind of exclusion effect needs to be better investigated. We were essentially using only minimum distance, and in reality there is a distribution of distances. So sometimes there will be by chance enough mass to have very massive objects close together, but it's not very likely. We were using just a sharp minimum distance. So there is still room for improvement, but I think that this is the first time such an exercise has been done of producing catalogues in this precision. And we also did it for 10 redshift snapshots, so producing the cosmic evolution of all the catalogues. And you can see a wonderful agreement between data and our mock catalogues in terms of the correlation function and the quadrupole. I should mention that the curves which are not on top of the data are due to a different set of mock catalogues, the so-called QPM mock catalogues, which were, this team has been really useful, helping us also a lot and contributing. They have written the codes to produce the geometry of the survey. We are on the same boat, but essentially they neglected cosmic evolution in their mock catalogues and had a more rough bias description by just using a rank ordering most massive objects in more high density regions. And as you saw before, that's not true. So we are in this respect doing better. And also we calibrated the peculiar motions of the galaxies in different snapshots. So that's why the blue curves essentially are on top of the arrow bars of the data for different snapshots. Here, in this high redshift mass bin, you see that both catalogues are performing well in terms of two-point statistics. And here you see the same in Fourier space. We are performing the blue and the red are our catalogues, the PATCHY catalogues, and you see that we are in very good agreement with the data. And here in this upper plot, you see the three-point statistics, the three-point correlation function in configuration space, and essentially the red, the data points are the dots with the arrow bars, and the red shaded region represents the reference embody-based catalog, and our effective bias catalogs are represented by the blue one. So I think it's pretty impressive that we are at the level of an n-body simulation also in terms of three-point statistics, and in this case even better. Okay, and it's also interesting to see, and this is actually the reason why we do this whole effort, how the covariance matrices evolve for different redshift snapshots, because these covariance matrices are a crucial ingredient to estimate error bars in the analysis of the BOSS survey. And this is the first time that the cosmic evolution of such covariance matrices has been computed. And if it's maybe hard to distinguish now with the screen, but actually this this diagonal part is more sharp at higher redshifts here between 0.55 and 0.75 than at lower redshift where it gets broader, essentially already indicating that gravity has coupled modes in a more strong way, and the covariance matrices change. So this is important if we want to do precision cosmology. Something which we don't really understand is this part which is related to the quadrupole. As you can see, there is an evolution, and then so it becomes stronger. These off-diagonal terms become stronger, and then they disappear again. This kind of evolution we don't fully understand, but we find it interesting. It definitely needs to be further investigated. And we are also working on a comparison study of covariance matrices with different methods, actually including Claudio Della Vecchia from the IAC, and trying to understand all these things better with a set of n-body simulations, with approximate methods, etc. Well, and one very interesting application which we can do because we are precise in the higher order statistics with thousands of mock catalogs was to measure for the first time the baryon-acoustic oscillations from the troughs in the density field. I was very excited about this work because essentially we are not observing voids. So this let me use an analogy. If somebody tells you these are the white squares of a chessboard, tell me where are the black squares. That's redundant information because it's just the complementary information. So that would not be enough. You know perfectly well where are the black squares if you know where are the white squares. The analogy is more like if somebody would give you the positions of white figures in a chessboard and would tell you, well, you know the rules of this game. What is the most probable distribution of the black figures? And then if you reconstruct that, you will understand better the game, right? So, but you're not observing the black figures. We are not observing the voids. That's not an information. It's not really independent information from the galaxy distribution. We are constructing from the distribution of galaxies in a geometrical way where are the minima of the density field in the void regions. And that information is encoded in the higher order correlations of the galaxies. So what we are doing is transferring information from higher order correlation, from higher order statistics, from galaxies to the 2-point statistics. And this is interesting because this is an alternative way which is less subject to cosmological assumptions than in what you do in BO reconstruction. Which I guess many of you know, where people essentially say, I want to increase my baryon acoustic oscillation signal, and since I have a physical model, I know that gravity has coupled modes and has erased that signal. I can use the distribution of galaxies to infer the displacement field, go backwards in time, and linearize my density field, and have a higher BO detection. And let me mention that the 3.2 sigma detection is roughly what you gain with BO reconstruction from the pre-reconstructed baryon acoustic oscillation to the post-reconstructed one. And I would like to highlight the wonderful work done by Kia-Sun Chuang, Yu Liang, Cheng Zhao, Xiaoling Tao, and also the BOSS collaboration discussing all these issues. Okay, so this is the time to go to the second part of the talk, which is inference of the cosmological large-scale structure. So now I have discussed for a while how we can accurately model the large-scale structure, the distribution of halos, the distribution of galaxies with these effective models. Let me say that there is still a lot of work to do. We haven't analyzed all this with emission line galaxies. We have been working with rather massive objects, so there is still a lot of work to do and things to investigate. But I think it's very promising. We know how to do it for massive objects, for luminous red galaxies. We are confident that with the same kind of approach, we will manage to do a good job for less massive objects. Now, how could we use all these approaches to do inference of the cosmological large-scale structure? And this is equivalent to ask, let us reconstruct the particular realization of the universe we're looking at. Not just in a random way produce different realizations, but really consider the particular one we have from the data. And this is a complex problem. Essentially, we need to consider that there are a lot of variables which are coupled together, and a joint analysis is required. So in principle, as I was saying, the endpoint functions, all higher order statistics, determined by a physical model, essentially gravity, will determine the dark matter density field. We have, on the other hand, the bias of our objects, halo or galaxy bias. We have peculiar motions because we observe things in redshift space, and all these, and then at the end, the data are data in redshift space. So in principle, we need to solve a joint problem, and this can be approached in a Bayesian framework, where essentially, for instance, if we just assume that the 2-point statistics is enough, then the density field, what we could call the signal we are interested in, conditioned on the data we are observing, would be determined by the 2-point statistics, covariance matrix, and the peculiar motions if we know them, because then we could solve for, we could do the mapping from redshift space to real space. And then in another step, if we know that signal, we could infer the correlation functions, the covariance matrix. of that signal. And if we know the signal in real space, actually, we could infer with some models the peculiar velocity. So there are ways to do this in an iterative way, actually, and a lot of work has happened in the last decade, starting from Gaussian statistics, also in the CMB, where they use these Gaussian statistics to improve, to go a step further and do this global analysis, to really work with non-Gaussian, non-linear statistics. There is already a bunch of literature, but still a lot of work to do. So let me just flash this in and go on. I was discussing about this stochasticity, that it's not a simple Poisson model. And actually, we implemented this in this Bayesian framework. You can see here the dark matter density field on the left-hand side, a slice of the three-dimensional distribution of a box from the Bolshoi simulation. And here you see the corresponding halo catalog on the same slice. You can see that it is very noisy. You can see that some structures or the prominent structures are there, but of course you have this loss of information I was describing. And the question is, now let me just ask in terms of two-point statistics and cell-to-cell correlation also, but let's talk about two-point statistics. How can we infer the unbiased dark matter density field? Okay, just let us consider the models which have been successfully applied. By the way, let me say that in this exercise we are applying those models already to lower mass objects, already in the direction of emission line galaxies, but maybe not fully, going down to 10 to the 9 solar masses. And let us consider the non-Poisson distribution function. In this case, it's the negative binomial distribution function. You could use another one like the gravitothermal dynamics probability distribution from Zaslav and Hamilton, but essentially you have a probability distribution function with one parameter which controls the deviation from Poissonity. And we showed that both have are equivalent if you make the proper transformation. So essentially, this parameter controls that deviation. And if you do the whole analysis with this bias model, assuming a very simple prior for the distribution of the dark matter density field, namely that it is log normal distributed, meaning that the logarithm of the density field is Gaussian distributed, then you will go from this power spectrum over here, the M-body simulation of the halos. So this is the power spectrum as a function of K modes. You will get this green curve here. And if you do the whole reconstruction process, ignoring the deviation from Poissonity, you will get this curve over here. Now, the dark matter density power spectrum is the black curve. So you see there is a deviation which is of 20% at k equal 2, 0.2, k equals 0.2. So that's already a relevant scale for baryon acoustic oscillations, and the deviation is just too large. If we model this deviation from Poissonity, we can be on top, and that's the shaded blue region. And you see that we can be unbiased almost up to k equal 1. So that's already one example how what we have learned from forward modeling, for modeling in calibrating and comparing with embodied simulations, can be used in an inference analysis. Now, of course, we also need to correct for redshift space distortions because the data are affected by their peculiar motions. You know that on large scales, galaxies tend to fall into the gravitational potential wells. These are called coherent redshift space distortions and have the effect of squashing structures on large scales, the so-called Kaiser factor. However, on small scales, you have quasi-virialized motions of galaxies. You have all these satellites moving very fast, like almost gas particles, and that produces the contrary, elongation along the line of sight. So squashing along the line of sight and elongation depending on the regime you're looking at. And these are called fingers of God, which is a funny description, I think, from Brent Tully many decades ago. So in this Bayesian framework, you can iteratively solve for these effects. You can see the two-dimensional power spectrum now to study the anisotropy produced by redshift space distortions. And you can see the true isotropic two-dimensional power spectrum by the different color code shaded regions, essentially computed from the AMOC galaxy catalog in real space. And the dashed curves would be the equivalent in redshift space. So you see that perpendicular to the line of sight, there is no effect. However, parallel to the line of sight, there is more power on large scales. So what we see in this plot is essentially this Kaiser factor. And iteratively, we can correct for that and become very close to this isotropic one. Okay, so this is the machinery. You want to recover the density fields. You want to recover the real space positions. So essentially, we can produce a set of real space positions. This is a way of using the three-dimensional distribution of the galaxies and our theory about density and peculiar velocity fields to infer the true distances to galaxies, which I think can be useful for observers. And you can produce many catalogues which are compatible with the data in this way. So this would be like the real space positions of galaxies based on the redshift space positions. Once you infer the peculiar velocity field conditioned on the reconstructed density field in a previous step, and which will depend also on the Hessian, which is a non-local quantity, etc., on the growth rate, which you can also sample, etc. And you can also sample the completeness, like the window function, the completeness, which will be affected by the true positions of the galaxies. So there will be slight differences precisely in gradients, sharp gradients of the selection function. And you can also iteratively sample the correlation function. So just to flash in, the probability distribution function we are sampling is this one. So it's rather complex, despite of the fact that we are, in this particular case, only considering the two-point statistics. The log normal assumption and this negative binomial distribution function considering this nonlinear bias with threshold bias, etc., stochastic bias, etc. Well, yes, and this is an application to the BOSS data. So you see here the CMAS galaxies computed on a grid, and you see the overdensity field of observed galaxies. You see here the corresponding completeness, and here you see the mean over 4,000 reconstructions with this Bayesian Gibbs sampling algorithm. So you see that there is some kind of noise here because in each sample you are augmenting the full volume. But of course, if you integrate, if you compute the mean over many realizations, you don't have information here. So those samples, that information should disappear in the mean. But you can go a little bit farther due to the further inside the region close to the boundaries because you have information due to the correlation function. So if you're already in a peak, you know that it will not be sharp. That's an artificial artifact due to the mask, to the survey geometry, to the selection function, but it will, according to the correlation function, continue. And the contrary, the same happens with low density regions. And essentially, I should say that this is also the real space density field. There are many applications. We get the peculiar velocity field, we get the density fields, you can do improved reconstructions of the displacement field, etc. And just more quantitatively, here you see we have done the exercise not only on the data, but also applied on mock catalogues. And in redshift space, you see that there is the quadrupole deviates strongly from 0. And the green one would be the mock catalog in real space, and we can recover it very well. And you can see here the power spectrum, how we get the nonlinear power spectrum, essentially correcting for mask effects, etc., because this is the one from the data, actually. Okay, so let me go quickly. I think I should finish soon, right? 5 minutes, very well. So if we want to do the whole analysis in a more complex way, we should include higher order statistics. You can already see that it becomes very complicated. And on top of that, you need models for those higher order correlation functions, 3-point, 4-point, etc. It can be done, but it's very tough. Is there a way to include a physical model? And the answer is yes. And let me show what the concept of it. So what would you do if your favorite cup dramatically breaks into pieces? What would you do? A question to the audience. What would you do if this happens? Glue it together. And would it look as good as it looked before? Alternative? Buy another one. Buy another one means do the whole process not inverse, which is unrealistic, but forward. Because there is no other way. It's actually an irreversible process, okay? And we can actually do that in this analysis as well. We can do the analysis in the initial conditions, and which are very well described by the 2-point statistics, rather than doing the analysis in the final conditions where higher order statistics are introduced by gravity. So one example is this kind of Bayesian approach in which you iteratively sample the initial tracers corresponding to observations. I cannot go into details. If anybody has questions, I can answer them afterwards. Essentially, here I do the exercise with the De Lucia mock galaxy catalog, and iteratively I sample the Gaussian fields where the 2-point statistics is enough. And with perturbation theory, with this kind of fast gravity solvers, I can produce the final density field and see the matching between the density field and the observed galaxies. And then I can produce the Gaussian PDF in contrast to the non-Gaussian PDF at final conditions. I can compare to the Millennium Run, which was used to produce the De Lucia mock catalog, and see that I get an unbiased reconstruction of the initial Gaussian density field. I can see that I reproduce the initial linear power spectrum, including the features, the particular features of the realization of that, in this case, simulation, the Millennium Run. And you can see that we get unbiased results. This difference is just due to the mass assignment scheme used in the redshift 127 I used from the Millennium Run, which has aliasing, but we do not have aliasing because in our formalism we sample the Gaussian field. Okay, so you can also apply this for cluster analysis. We will submit very soon a paper with Patrick BOSS, a PhD student in Groningen, where this framework can be used also to study the filaments connecting clusters and the mapping from redshift space to real space. And let me just finish with some applications of this method. So here you see the power spectrum of data, of real observations. It has shot noise, it's non-linear, it has some bias, but since we have a model for the initial conditions, we can reconstruct the Gaussian fields of the initial conditions unbiased with our model and reproducing, however, the structures we observe. So here you see a constrained and body simulation. The dark shaded areas are the dark matter density field from that constrained simulation moved to redshift space. And what you see here are these dots are galaxies, Coma, Virgo, with a lot of fingers of God, by the way, Perseus Pisces, Norma, etc. Oh, and this would be a phase space reconstruction done by the group in Stanford in real space. So you see this accordion effect. Many filaments which are squashed get pop out when you go to real space. And you see very nicely here one of the prominent Virgo clusters. You can study the cosmic flows. Let me show a movie. You have the local group, you have the local void, Coma, Perseus Pisces, and actually you can see the streamlines, how starting from the center, we are actually moving towards Norma, which is what people observe from the CMB dipole. And you can do this analysis and compare the direction and try to understand the CMB dipole we know because of the cosmic microwave background. We have also studied cosmic flows and found a nice agreement by embedding our reconstructed constraint sample in hundreds of larger volume simulations, and we have used that information of the cosmic flows to reduce the error in the distance measurements from supernova in the very local universe, and we found a reduction of about 2%, which is already making them more closer in agreement with CMB results. However, we know that the disagreement is about 4–5%. There is another work by Rigaud et al. Where they say that also environmental effects of where the supernova explodes in the galaxy can have an impact of a few percent. So maybe the combination of both could give an explanation. But I should stress, this is going only until redshift 0.025. This is very local. We can do a study of the local universe. People, Karashentsev et al. Had assumed that, or from observations, stressed that there could be a problem in the fraction of matter in the local universe. Actually, if you do these constrained simulations where you get the full dark matter field, because you are not only focusing on particular objects, there is this information loss, right? There is a lot of matter outside in the rest of the cosmic web. We find the same features as the observers find, but actually a good agreement if we consider the full dark matter field, and a good agreement if we just start to consider only halo populations of different mass spins. We can do an environmental study. There has been a lot of interaction with people from the IAC here. What is the environment in which ellipticals reside, or spirals, or extremely metal poor objects, etc., voids, sheets, and so on. And this is just a picture to flash in. You see the galaxies, a sky plot of it, and the underlying dark matter field with augmented Lagrangian perturbation theory, and then the constraint simulation, so which we have been used in these studies. So you see a nice agreement between one and the other. And you can use that to study the warm-hot intergalactic medium. You can use velocity fields to study the kinematic Sunyaev-Seldovich effect. All these works I should mention also in collaboration with people from the ISC, Ricardo, here Ricardo and Jose Alberto, and so on. And just let me finish with this picture we had in National Geographic by doing a phase space representation of this constraint and body simulation and the structures around us. Okay, so these are my conclusions. The galaxy distribution in redshift space encodes information of the full phase space, and you need just some assumptions which are very reasonable, like the primordial fluctuations are closely Gaussian distributed with a given power spectrum, and the universe is isotropic. And then you can recover the full phase, nonlinear phase space, velocity fields, etc. You have seen that there are efficient gravity solvers which work moderately well on megaparsec scales. And I have also discussed different effective bias components, which are very important to take into account. And also regarding the stochasticity, the deviation from Poissonity. And also, I have discussed the Bayesian framework in which you can do this analysis, and there are a bunch of applications. You have seen many of them, and I think there is a lot of work to do still. So thank you very much.
Thanks, Paco. Are there any questions in the audience?
So related to your latest simulations of the nearby universe, let's say, so how far you can go into the zooming of those simulations? For instance, I'm thinking on if one wanted to study the history of the comma cluster assembly, for instance, one could go back and to which scales? So
I think the comma cluster, which are actually we were very excited about the comma cluster because we reproduced the mass within the observational error bars of the comma cluster. This work was done by Stefan Hess. If you need, of course, to pick up those solutions which are most compatible with the observations. We got different results, but you can do a posterior cross-correlation analysis and pick up the constraint simulations which are best correlated with observations, and then say, okay, this one I trust more, and then you can study the cosmic evolution of that cluster or object.
So, yeah, but how far you can go into the zoom, into the simulations?
Into the small scales.
I mean, you can trust the evolution
of... there are a couple of problems here. One is the bias, galaxy bias. The other one are the redshift space distortions. Actually, these fingers of God are terrible in these clusters. We have modeled them, actually. We have modeled those fingers of God and done them proportional to the local density, to the gravitational potential in those regions. But I think there is still a lot of work to do there, especially regarding the gravity solver you use in the reconstruction process. So when you ask me that, I should mention, besides redshift space distortions and bias model, it's also the structure formation model you use. I think you will need full gravity solvers to go to the very small scales. With this kind of corrected Lagrangian perturbation theory solvers, I think you can maybe study in a reliable way the very massive objects, but not going to the substructures.
Yeah, but nothing prevents you, for instance, to model, let's say, the local group, 2, 3, 4 megaparsecs sphere. If you were having, for instance, a lot of, small galaxies to trust well the mass distribution. So in principle, it's not a matter of the scale, or there is some limit. I mean, if you were having, let's say, 1 million galaxies in 2 megaparsecs, you would be able to trace back this?
I insist. It's the gravity model. Once you go to those small scales, it's not only the gravity model. Having a precise gravity model is not sufficient. You then need to accurately deal with the bias of those objects, because they will not have exactly the same bias, and they have different properties, different masses. You have to take all that into account, and that is something which has not been done until now. I mean, there's, and I assume that in the future we will, there will be an effort in different groups to address these issues, because they are interesting, and we will need to do convergence analysis and things like that with different approaches. So I think there are really many assumptions in this kind of reconstructions, much more than when you do just an n-body simulation. So those have to be very clearly stated, and you need to really each sector, like gravity model, redshift space distortions. Redshift space distortions, not all the objects will have the same peculiar motions. We were, in this work, for the first time, considering at least the quasi-virialized motions, but not distinguishing the objects, saying statistically any object could have this kind of random component. And it was a very particular Gaussian streaming model. So I think there is still a lot of work to do, and it has to be calibrated, cross-correlated with embodied simulations, and then applied to observations. The pictures can look very nice. I think summary statistics needs to be analyzed. I think if you start getting masses which are compatible with some objects, that's very encouraging, but it's not sufficient. We need really a huge effort until I can answer your question sorrowfully, or maybe that's the luck. There's a lot of work to do.
Is there any other question?
Since no one else, that's a cup.
It didn't break.
It didn't break the cup. Well,
Okay. So
you can buy another one.
it's about the comparison between the three-dimensional reconstructions of the local universe that your numerical simulations provide, and the comparison with the traditional techniques that observers use to characterize the density, so like counting how many galaxies you have around them, and etc. Do they match? I mean, have you studied that thing? Because somehow I understand that your approach to determine environments is far more realistic than the ones that you can infer from counting galaxies. So eventually everyone will go through, I mean, will use these numerical simulations to determine environments. So, but how the two things compare?
Well, I'm convinced that there will be a burst of work in this direction, and people will start to use this as almost a standard thing to do. Essentially, there is a reason for this. If you look at the galaxy distribution, just their positions in space, there is. It's very difficult to infer directly from there the nonlinear density fields, etc. However, we have the point is that we have information, for instance, coming from the cosmic microwave background about the initial conditions, closely Gaussian, etc. We have theoretical models which support that, and we have a fair good understanding, at least in a certain range, of how gravity evolves from those initial conditions to the final ones. So using these two things, and also that the universe is isotropic in the initial conditions, closely homogeneous and isotropic, we can extract much more information. So it's not arbitrary, completely arbitrary in all cases, how galaxies are connected to each other, for instance, through filaments. There are, at the end, only a few solutions if you solve the equations of gravity from a Gaussian initial field to match those observations. That's why it's so powerful. There will be, in cases where you don't have enough data, where it's sparse and so on, there will be many solutions, fine. But in many cases, you will constrain much better the higher order statistics, and the phase space information, including the peculiar motions, in this kind of forward approaches, where you try to go from the initial conditions till the final one in a forward way, matching the data. So the comparison is I would say, answering your question, on very large scales, they should agree with simple biasing, but see, also the bias is a problem, because when you say counts of galaxies and so on, you will have the biased galaxy field. In this case, since we have a model for how the dark matter density field is distributed in the Gaussian regime, we can use that to produce the unbiased dark matter field compatible with observations. That's what you saw. We sample Gaussian fields which are unbiased. Actually, we use a Lagrangian bias to fit the linear power spectrum in the initial conditions. We really want to be unbiased. The features determined by the faces of those big objects are constrained, but the overall shape should be unbiased. That's our model. And then we produce unbiased density fields. So that's also another difference to the classical methods.
Okay, thanks, Paco. So if there are no more questions, let's just remind that coffee is in the cafeteria now, so it's probably getting cold, and let's thanks Paco again.